Hello, dear audience, and welcome back here on our industry stage at Formnext 2023. Day 4 and still so many highlights to come. If we want to achieve stability in products and processes in additive manufacturing, we need suitable methods to assess the quality of the influencing factors. One possibility is to use X-rays to assess material properties. Since I'm definitely, for sure not, an expert in this topic, but I'm highly interested, I am pleased to welcome Dr. Amir Khushias-Jabari, R&D staff scientist at Oak Ridge National Lab, someone who can definitely do this. His topic, deep learning-based XCT for accelerated non-distraction evaluation in metal additive manufacturing. Amir, I'm so excited to see you on stage. Stage is yours. Enjoy the presentation.
So, hello everyone, thanks for coming to my talk, and thank you for having me in here. So, I will be talking about our deep learning-based algorithms for high-throughput characterization and rapid qualification in metal additive manufacturing. So, current material qualification approaches in metal additive manufacturing are very slow. In fact, for nuclear application, we are looking at more than 10 years. So, there is a need to rapidly qualify materials. And for rapid qualification, we need high-throughput characterization. Characterization is critical for understanding the processing, the structure, the properties, and correlating them with the performance of the materials and parts that we are making. And understanding these relationships is what allows us to have consistent and reliable parts. At Oak Ridge National Lab, we have several groups that are working together to achieve this understanding. We have a group of material scientists who work on improving and optimizing the materials for advanced manufacturing of complex parts. They talk with us, they design the experiment. Our work is on automating the high-throughput characterization. So we get those design of experiment and prints and characterize them. And the output of this characterization, the design that we have, goes to a digital team that has all this data plus in-situ monitoring data that we get from the printer, all the mechanical testings, and then they have created a database which we have actually published a lot of this data online in recent few months, and they also analyze this data and they give feedback to material scientists. They also talk with modeling team, and then together this allows us to have an understanding of the process structure property performance relationships and help in designing better parts. So here is how our high throughput characterization systems work. We have been collaborating with Zeiss on a design that you can see in here. It's more complex than the cubes that you see in most of the additive manufacturing papers at least. So this design has a cylinder at the bottom with some geometric features which allows us to understand the relationship between process parameter and geometry of the parts. Each one of the coupons that we print has a separate process parameter in here. So you are seeing here 36 different coupons, each one of them with a separate process parameter. Then we CT them. The process in here is we load the 10 samples at a time. We scan very quickly scan, and that's one of the key achievements that we have in this project. So we scan one sample. Immediately the output goes to a computer that again quickly analyzes this data, perform reconstruction, segmentation, output that, and then the next scan begins. And this process automatically is being done. The output goes to our in-situ monitoring software, which is called Peregrine. Together, this is all registered and goes to our digital framework. We also select samples and we do microscopy, and then those also will be registered to our again, digital framework and the data that we have, and we do the analysis on all the data. So this quick scan is a critical part, but when you have metals, quick scan is very challenging. So our algorithm allows that quick scans produce very high quality output, and that's something I will show in here. So let's define what we mean by a reconstruction and a segmentation. So here, when you do a CT, you have a part, you put in a CT system, the output that you get is a raw measurement. It's like an X-ray microscopy, X-ray image that you get from in medical imaging. So in the CT, you have a lot of them from different angles. You need to perform a reconstruction to create the 3D object. That's one algorithm that you need to have. The second algorithm is once you have the reconstruction, you need to perform segmentation to analyze these flaws, the anomalies in there, and the dimensionalities and everything. So there are two sets of algorithms that we need to develop for reconstruction and post-processing. And we have been developing a deep learning-based algorithm for both these steps. Here is another schematic of the XCT system. The traditional reconstruction algorithms are either analytical, that are the thing that you see in the CT system currently are analytical reconstruction. This is not what the best you can get, but this is the fastest you can achieve with the CT system. And in academia, we have iterative approaches which are much higher quality, but they're very, very slow, so it becomes not usable for real applications. In addition, when you are dealing with metals, everything's actually become much more challenging. I should put some example in here. I don't go through all of them, but you can see the complexity make a problem. If you want to understand the defects, you might need even 7-hour scan on a very small, tiny part of the sample to understand those defects. So these are all challenges, and we have been trying to use these deep learning-based algorithms to address these challenges and improve the quality. So our reconstruction framework, we call it Simurgh. It's an XCT reconstruction framework that has helped us achieve several things in the past few years. We have reduced scan time and cost. We have improved the reconstruction quality without compromising the time. We have lowered the cost of implementation, reduced the maintenance needs with faster scans, and also enabled high-throughput scalable characterizations. All of this, because of the high quality of the data, we have also enabled post-processing that are much easier to do with this high-quality data. Let me give you an example. Here, you are looking at the same geometry that I was talking about. This is 15mm steel. Most of the presentation that I have seen in the past few months or years in the conferences, small cubes, 5-6 millimeter is what you see in the CT system. This is 15mm of a very dense part, which requires 1 to 2 hours of a scan on a high voltage CT. Let's assume here we have done a 1-hour scan on this sample and we cut through it to look at how the cross-section looks like. You see a small defects in there with a 1-hour scan. It's still very noisy. You can do some post-processing to improve that. But 1-hour scan, if you have hundreds of samples, is not feasible. You cannot do hundreds of them and analyze them and send it back. So we need to reduce the scan time. We go to a 10-minute scan. It's a factor of 6 hours. Everything becomes noisy, the defect is gone, and it's not really usable. This is what you get from our algorithm with a 10-minute scan of these samples. The same sample, the same. So I think the image speaks for itself, and then this has allowed us to, we have received Department of Energy Technology Commercialization Fund Award. We have a non-inclusive licensing with Zeiss that they are using this software right now, and we have patents and paper for this. So just a small touch on what is the method. I don't go through the detail, but we have under the hood 2 different frameworks that we are using. One of them we call 2.5D CAD DLM-BIR. This is in a nutshell, in a supervised deep learning approach. The key idea in here, because in additive manufacturing we have the CAD model of the part, we leverage that to produce very high quality ground truths and train the neural network to remove the artifacts from low quality data and produce high quality data. Here, we need some ground truth data that we need to train. The second network is actually everything is synthetic. We have the CAD model. We use generative adversarial network. We design this network in a way that we can generate a lot of data. We don't need even any ground truth data to acquire, and then we can have this synthetic data to train the network and then use it for testing on real data sets. This one on the left is the one that we have been consistently using and producing very high quality data. And the second one is something that we are working to put inside the CT system and reconstruction frameworks. So let's look at some of the results that we have achieved with this one. Here you are looking at the CT of an aluminum sample, a simple maybe sample, a lower density, but the same thickness. Again, we are looking at the 15mm at the bottom. If you look at the cross-section with a 30-minute scan, which we standardly use, that's what you get on the top right. But then this is with 10-minute scan, this is what you get from our algorithm. Just that maybe not enough. We looked at the 64 different samples. We characterized them individually, and then we look at the density extracted as a function of sample number in here. Here, we did pycnometry. The stars in here are the density extracted from pycnometry. And the circles that you see, blue and cyan, is red and cyan, is what we get from our algorithm. And the squares are you get from a standard algorithm, which 3 times a slower scan. So the key in here is not only the quality, it is the consistency of the reconstruction that allows us to follow the trend, because we know picnometry may be not the perfect ground truth, but it allows us to follow the trend in here, while with the standard algorithm, there is all over the place, and we need to fine-tune everything to get the results. Now we go even a step further. Here we are looking at the inconel. Inconel is 2.5 times denser. It is much more problematic for CT, and typically we need a 2-hour scan with the same sample that I just showed. Here we did a 10-minute scan. FDK is what is the standard algorithm is giving you, and these two are results. So to quantify what we are doing in here, we cut this sample, we did microscopy and 1 micrometer pixel resolution. We registered that microscopy to our CT data, and we look at the detection rate. Here you are looking at the detected flaw as a function of their equivalent diameter. So you are looking at probability of detection as a function of diameter, and you can see green and red are results compared to a standard result with the same time scan. We are detecting more than 90% of the defects that are 80 micron and higher, while with the standard technique, the same timing, the same segmentation approach that we use, this standard approach, it's more than 300. So it is a huge gap between the two. And we also detect a lot of more pores that are at voxel resolution or sub-voxel resolution in here. And again, this is an inconel sample, 15 millimeter, very dense sample, not very easy to scan. So we went one step further. We are looking at the generalizability of the approach, because a lot of time people get a deep learning from a vendor, they need to retrain it. We don't say we cannot retrain ours, but we are trying to make it as general as possible so people can use the same technique across their data. So I show some examples in here. This is one example that we took from Nikon system. So we took a Nikon system. This is a standard reconstruction with a 20-minute scan. And then this is our result with 20-minute scan. At the beginning, it looks like so many things in there. But now we did the same sample, 200-minute scan. It's 10 times slower. And we did reconstruction with a reference iterative reconstruction, and we look at the data. And I think, again, the figure speaks for itself for this data. And this is for the Simurgh. For the network that we are using currently in the system, we have also a lot of analysis that there. I just put some of the images in here for visualization, but there are more if you want to ask questions later. But we looked at the geometry independence, material independence, scanner independence for this sample. Here, we trained the network with our samples that you see in here. The sample is the same Zeiss geometry, we call it. It's a still sample for training, and it was a scan on a Zeiss system. And then the test sample is a different geometry, different denser material, and a Nikon scan. And again, we cut through the sample, we show some images in here. In fact, in our collaboration, we are using a single model across 7 different materials so far, and all of them has produced very consistent, very high quality results. So what else we can achieve with this technique? Because it's the high quality of the technique, it allows us to avoid a lot of hand annotation. People right now, to annotate their data, to segment their data, they need manual labor. But here, because of the high quality of the data, we can generate very good annotation for our reconstruction and then train segmentation network. In fact, we are looking here as a porosity as a function of sample number for 36 samples. We showed the gap for one of the segmentation approaches that we had compared to our deep learning segmentation that was trained on our data. And again, you can look at the difference between the two segmentation in here on the right. So where we are using this, the first one is for high-throughput characterization. As I noted in here, we have 128 samples in here as aluminum. We scan them at fraction of the time. We reconstruct them as a fraction of time. And because of the high quality, the post-processing is significantly faster. Here, you are looking at the porosity at the top graph in there as a function of process parameter. What it allows us to look at each one of these and say, hey, where is the best process parameter to give you the least porous sample? And that's for the whole part. the beauty of these samples are we can look at the geometry dependence. Now we can look at each one of these features and see a different process parameter depending on the geometry of the sample, which the graph at the bottom. It shows you if you look at the rods or fins or inclines, you have a different process parameter that optimize your based on the geometry. And this is a paper that we published in Nature Computational Material recently. Where else we are using it? Under AMMT, or Advanced Material and Manufacturing Technologies program. This is a nuclear program. We have been developing this automated high-throughput characterization to qualify fully dense 316 materials and understand this process structure, property, performance relationships. This is how the entire process works. We have the XCT data, microscopy data. Our team has registration to the in-situ monitoring data. So you have all the data in the same coordinate. Then you will have the other modalities, mechanical testing, and all of that work together to allow us to understand this process parameter. In fact, under this program, we have analyzed more than 540 coupons printed on 2 different systems, and M2 concept laser and Reneshaw. And we have looked at 2 materials, 316 and 316H. Here are some of the results that we achieved. On the M2 concept laser, we looked at 252 parts of these samples, and we characterized them. Here at the top, you are looking at the porosity as a function of energy density. We look at the window that minimizes this porosity, and then in there, we look at the microstructure, and we identify 2 characteristic microstructure for future testing. But the key in here, that the message for this slide is that we have this microstructure present that might be present in complex geometry, both of them, which invalidate the traditional qualification frameworks. And I think this is one of my favorite slides. We look at the 390 samples printed with Reneshaw. Here we did 20 minutes per scan per request of the people. And then it takes, just in terms of putting into numbers, with these so many samples, it's a factor of 6 faster everything. But the thing that we achieve in here with Reneshaw system, every graph in here, each axis is a different process parameter. And the line, the dashed line and a solid line is the gap between the 0 to 0.1% porosity. And we plot that for different features in here, full part versus the geometry. And looking at all of them together, we can look at the gap in the white region to tell us which is the region of optimum process parameter that we consider everything. This is, of course, on this data, we can expand on our process parameter, and we can analyze this more complex, do more complex analysis. So, in summary, we have enabled faster scan with lower cost and labor. We have higher the quality at no computational cost. We have enabled high-throughput non-destructive characterization that it can pave the way for Industry 4.0 application once we connect it to the printer and give feedback. A single model for multiple materials, and we have, because of the high quality, we enhance detection and reduce analysis. And there is, of course, a big team behind all of these efforts that you can see all their names. It's a collaboration with ZEISS and also Raytheon Technologies. Thank you.
Awesome, Amir. Awesome. I have a question from the audience directly. It sounds a little bit critical. I don't know. It's from Josh. So the question would be a more broader conceptual question. As a production engineer, I want to get rid of CT scanning each and every part, especially with small lot sizes or of highly individual parts. It seems to be the only way still. How can we reduce the amount of samples scanned in general? What's your opinion on that?
That's actually a very good question. We are achieving that at Oak Ridge. The ways like these high quality CT data give us very high quality data for in situ monitoring. So we use them as a ground truth for in situ monitoring to improve our in situ monitoring process. Once we improve our in situ monitoring process to get to a good detection capability, then we can get rid of that and use that as our process. And that's what actually in a paper recently we published, we showed that we can detect 90% of the part, 90 defect in situ with more than 200 micron or so. So that's actually we have working on. Yes.
But that's another good question. For the in-situ monitoring, are you working together with companies that are offering that, or is it something you develop yourself?
So the thing is, like one of our groups is developing their own, but that has been licensed by more than 35 companies. So it has been so successful in the past few years, and that's our baseline. But again, we can work with other companies to do that, and that's part of it.
So you deliver the databases in order to make in-situ monitoring better and better and better and better.
Yeah.
And so How many companies are already using this new method?
For now, it's only Zeiss, but with our collaborators, for example, with Raytheon and others, we are using with their system that is not Zeiss system.
Very good, very good. So this was it so far from my question. Any more questions here from the audience? No? Then Amir, thank you so much. It was a pleasure to have you here on stage. Good luck, and thank you for the presentation.
Thank you.
Bye-bye. Yeah, ladies and gentlemen, exciting last day here at Formnext on the industry stage at Formnext 2023. We will cover in a nice and interesting panel after the highlight break, we will cover a little bit more the topic of design for AM and try to get everything clarified that we discussed the last 3 days. So please stay tuned, enjoy the highlights, and we'll see you in a few minutes.